To tell you a little bit about our speaker tonight, Dr. Arney is a research space scientist in the Planetary Systems Laboratory at NASA Goddard Space Flight Center. She has interests in planetary atmospheres, astrobiology, and exoplanets. And she presently serves on the Venus panel for the ongoing Planetary Science and Astrobiology Decadal Survey. And previously, she led the science support analysis team for the LUVOIR, which is the Large Ultraviolet Optical Infrared Observatory Astrophysics Flagship Mission Study. Dr. Arney, she picked up a dual title PhD in astronomy and astrobiology from the University of Washington back in 2016. So won't you please welcome tonight, for the first time at the Westport Astronomical Society, Dr. Arney, who is co-deputy PI of the DaVinci project to Venus. Welcome, Dr. Arney.
Thank you all. All right, let me go ahead and share my screen. All right. And those are really cool astro photos that you're showing. Those are fun to see. So I'm Giada, and I'm one of the co-deputy PIs of this newly selected mission to Venus called DaVinci. And I'm happy to be here tonight talking to you all about some of the most exciting things that I think our mission is going to do. Let me just move this Zoom window real quick. It's like blocking half my screen. There we go. So I think it's really exciting to be a planetary scientist who's aiming to better understand worlds within and also beyond the solar system. The worlds within our solar system are diverse and they're fascinating and unique, and they're close to us so we can study them in detail. And now we've also discovered almost 5,000 planets beyond the solar system. But I think, in this multitude of worlds, there's a lot of reasons why Venus is so special. It's special in part because it's the closest planet in the universe to Earth. But also Venus is special because of some of its characteristics and its past. There's a history to Venus that may allow us to understand some of the characteristics that make Earth unique in the solar system today. Obviously, today, Venus is dramatically different from Earth in many ways, but a lot of us wonder, was it always that way? And the previous missions that we've had to Venus have left open as many questions as they've answered. They've really only given us a glimpse of the Venus surface, as seen here in these views of the Venus surface from the USSR Venera probes that landed in the 1970s and 1980s. So we have a lot of questions that we want answered about this mysterious target. So we're really excited to go back to Venus. Now, before I launch in and start talking about the mission, I do want to just remind everybody about some basic properties of Venus, just in case you don't think about Venus like for most of your waking hours in the way we on this mission do. So to orient everybody, this is, as you probably know, a very extreme planet. The clouds are made not of water, but of a concentrated solution of sulfuric acid and water. Sulfuric acid is a really good desiccant, so there is a little bit of trace water vapor in the atmosphere, but that really good desiccant, that sulfuric acid, sucks it up into the droplets. So that's why the droplets are composed of both of those. The surface temperature on Venus, if you were wearing a very protective spacesuit and you were standing on the lowest lowland regions on the night side of Venus, and you look down at the terrain, you might actually be able to discern a faint red incandescent glow of the surface emanating heat it's so hot that you can actually see it in the visible part of the spectrum. Just barely, but if you look carefully, you might be able to see it. That's how hot the surface of Venus is. And the surface pressure is equivalent to being 900 meters underwater. So none of this makes for a very nice place to visit, obviously. But in the past, it might have been different. So there's chemical evidence in the atmosphere and on the surface, hinting these enigmatic clues that Venus may once have been more hospitable and maybe a nicer place to take a planetary vacation. So one of the pieces of enigmatic evidence we have is something called the D to H ratio, or the deuterium to hydrogen ratio. Deuterium is a heavy form of hydrogen, and this ratio on Venus is extremely elevated compared to Earth and other worlds of our solar system. People have speculated whether that elevated D to H ratio might be indicative of past water loss. And this is a really important piece of evidence for possible past water on Venus. So I'll speak more about it on just the next couple of slides so that you understand that story. There's also these very interesting and also still very enigmatic emissivity or heat measurements of certain areas of the surface that some people have interpreted as possible evidence of rocks that formed in the past from water-rock interactions. So these tantalizing clues together, they're hinting at something that we want to better understand. Now, of course, we don't know whether Venus was truly habitable in the past. So that's partly, why we want to go get more data to better piece together this mysterious history. So as the story goes, if there were oceans on Venus, as the temperatures rose on this planet, the water would have massively evaporated into the atmosphere to the point where you've evaporated all of the water on your surface into the atmosphere. And this is a process called a runaway greenhouse. The reason it's called that is because it's a positive feedback loop. Water is a greenhouse gas, so it heats the planetary atmosphere and surface. The more you heat the surface, the more water evaporates. The more the water evaporates, the more heating you get, et cetera, et cetera. So there's that positive feedback loop, that runaway greenhouse. And through this runaway greenhouse process, if Venus had oceans, this is how we think they all evaporated into the atmosphere over time as the planet heated up. Now, going back to that D to H ratio, which I mentioned, this is a really, this is the most central evidence we have that Venus may once have had oceans. So why is that? Like, what is this telling us? Well, when you have an atmosphere that's saturated with water that Venus would have had in the past if it lost its oceans, then you get water all the way up through the atmospheric column. The atmosphere is moist, and the water molecules can basically reach all the way up to near the edge of space, which doesn't happen on our planet because our atmosphere is much cooler. So the water condenses into clouds at a much deeper altitude and rains back down to the surface. But on a planet like Venus, undergoing a runaway greenhouse, you get this water at super high altitudes. And when you have this water molecules hanging out near the edge of space, when you hit them with ultraviolet photons from the sun, you can break them apart through a process called photolysis and split them apart. For a planet the size of Venus, or also the size of Earth, those lightweight hydrogen molecules that get liberated from this photolysis process are difficult for a planet this small to hold on to, compared to a planet much bigger like Jupiter, which has a very hydrogen-rich atmosphere because it has a lot more gravity. A little tiny Venus can't hold on hydrogen easily, so it gets lost to space pretty quickly through this process. So we think that if this story is true, if it did have oceans and they did evaporate into the atmosphere, Venus lost its oceans through this process that I'm sort of illustrating in a very simplistic way on this slide. Now, heavy water is a little bit different. All planets have a small fraction of deuterium compared to hydrogen, and some of that deuterium is locked up in heavy water, so HDO instead of H2O. That deuterium is a little bit heavier than hydrogen. It's about twice as heavy. So you lose the hydrogen to space pretty easily. The deuterium is still pretty lightweight, so you still lose a lot of it to space, but the planet can hold on to more of it relative to the hydrogen because it is heavier. So over time, you would preferentially enrich the amount of deuterium compared to hydrogen that the planet has. And so people have looked at this really anomalously high D to H ratio on Venus. And one of the compelling ways to explain it is this really, compelling massive water loss process, which implies that Venus had oceans in the past. So is that true? Well, we don't know yet, because the data that we have, while it's tantalizing, it's not conclusive. So we want to go back there and we want more data. We want to better understand, were Venus and Earth always different? Were they similar in the past and then they diverged over time? And also beyond our solar system, are there important lessons that Venus can teach us about analog worlds orbiting other stars, especially as we're entering this new exoplanet renaissance with the launch of James Webb that just went up into space? So we're sending this mission DaVinci to the Venus of today to help us understand the Venus of both the present and the past. And in studying these clues in the planet's atmosphere and on its surface, we really want to sort of piece together as much as we can of the mysterious history. And we like to think of it as kind of igniting a new Venus renaissance. And the reason why we think of it like that is because our mission is named after Renaissance thinker, artist, and scientist, Leonardo da Vinci. Okay, so let me now introduce you to our major mission phases. Our science measurements are going to occur in 3 major stages. We're aiming for a launch in summer of 2029, which I know feels far in the future. It feels far to me too. It's hard to conceptualize how long these missions take, even when you're on the mission team itself. And after launch, we've got 2 gravity assist flybys of Venus that are going to help set us up for the correct orientation for our ultimate probe descent into the atmosphere. During those flybys, we're going to be observing Venus with cameras in both the ultraviolet and also the near infrared. Our first flyby will be 6 months after launch, and then 2 years after launch in 2031, in the summer of 2031, we'll be dropping that probe into Venus's atmosphere. And that's really the heart of the mission. It's during that 1 hour long probe descent that we're gonna take thousands of measurements of the atmospheric composition and also take photographs of the surface once we clear the bottom of the cloud layers to help us to much better understand the Venus environment. Let me tell you a little bit more about our payload. So to answer these big unknowns about Venus, we want to be dropping this analytical and imaging payload into the atmosphere. So this is our descent sphere. This is, as I said, this is sort of the heart of the mission. The descent sphere contains 5 instruments, and I'll tell you more about each of these instruments on the next couple of slides. We've also got our carrier spacecraft that's going to be carrying the descent probe to Venus and also doing the flybys of Venus. And it has 2 instruments that it carries, both are cameras that are used for remote sensing of the planet. The instruments on the descent sphere are carefully packaged inside of the titanium sphere. It's about the size of a large beach ball or a small beanbag chair, just to give you a sense of the scale here. And a lot of folks ask, you know, what happens when it reaches the surface? Like, how long is it going to reach the surface? Given that our hour-long descent, right, that feels so short. But we're not required to survive surface touchdown, actually. We're not necessarily even expecting to survive surface touchdown. We're not slowing down. So when I say surface touchdown, you might picture more of a sort of dramatic event than something gentle. So it's possible we may survive for some amount of time on the surface. And in that case, we do have onboard resources that could allow us to continue to transmit data for an additional 18 minutes. But all of that is a bonus. All of the measurements that we take prior to that in the hour-long descent through the atmosphere, that's the data that we really want to get back and that we're going to be transmitting to Earth for sure. Okay, so let me now just quickly walk you through, or at least introduce you to each of our instruments, just so you get a sense of what we're bringing to Venus and what we're doing with these really cool instruments. So we have an instrument called Venus Mass Spectrometer, or VMS. It's led by Charles Malaspin, who works at Goddard with me, together with Melissa Trainer and Will Brinkerhoff, who are also at Goddard. It's based on a similar instrument that's on the Mars Science Laboratory rover. And what this instrument is going to do is it's going to measure a whole bunch of gases in the atmosphere, including noble gases, as well as key trace gases throughout the descent. And the sampling resolution on this is every 200 meters or better. So we're going to get a really high resolution view of the vertical profiles of these key gases throughout the atmosphere. VTLS is the Venus Tunable Laser Spectrometer. It's led by Chris Webster and Amy Hoffman, who are both at the Jet Propulsion Laboratory, or JPL, over in California. It's got 3 lasers, and those lasers are used to measure to very precise detail various isotopes of of hydrogen and carbon and sulfur-bearing species. And this is also going to measure that important D to H ratio to great precision. It's going to measure it to precision of 2% or better, and that's sufficient to resolve between some of the models that we currently have of the history of water on Venus. The Venus Atmosphere Structure Investigation Experiment, or VASI, this is a cool instrument because it basically sort of wraps around all of the other instruments in terms of the data that it takes. It's going to be providing context for all of our other measurements that we take in the atmosphere, because it's going to measure pressure, temperature, and winds. And we need all of those data to provide context for our other measurements. The two cameras that we have associated with DaVinci are led by Mike Irvine at Malin Space Science Systems, together with Brent Boss, who's at Goddard. One of them is Vendy, which is a camera that sits at the bottom of our descent sphere. Vendy is going to peer through a sapphire window located at the bottom of the sphere, and it's going to snap photographs of the surface once the probe gets through the cloud layer. It's going to provide the very first photographs of a very intriguing region of Venus that I'm going to tell you more about later on in this presentation. And then we have Visor. Visor is a camera that lives on our flyby spacecraft. So it's going to be imaging Venus from above. It has filters on it that are going to image the clouds in ultraviolet light, as well as image heat emanating from the surface on the night side in the near infrared. Cubis is a technology demonstration instrument called the Compact UV Visible Imaging Spectrometer. It's led by Valeria Catini, who's now at the Italian Space Agency, as well as Ish Aslam, who's at Goddard. This instrument is aiming to measure a very enigmatic and mysterious compound in the atmosphere known as the unknown UV absorber. As you might infer from the name, this absorber absorbs ultraviolet light, and its identity is unknown, hence the name unknown UV absorber, very creative. This compound has frustrated planetary scientists for decades because it's a really important compound in the Venus atmosphere in that it absorbs fully half of the sunlight that hits Venus. So huge fraction of the light hits Venus, but we still don't know, after decades after discovering this compound, exactly what it is. We have all sorts of candidate compounds that it might be, but we still don't know which one it is, or if it's a combination of them. So hopefully with this instrument, we'll be able to shed light on that, on whatever that species is in the atmosphere. And then last but definitely not least, we have a student collaboration experiment called VFOX, which is the Venus Oxygen Fugacity Sensor. And I love the logo of VFOX with the cute little fox. It's led by Noam Eisenberg, who's at the Johns Hopkins University Applied Physics Laboratory, together with Sarah Hurst and David Kramer, who are also at Johns Hopkins. This is a little small ceramic sensor that's going to sit on the outside of our probe and measure oxygen in the deep atmosphere. And what's really cool about this is it engages dozens of students throughout the mission lifecycle. Okay, so that was a whirlwind tour of our instruments. And with this instrument suite, we're hoping to address some of these big questions about Venus. So let me speak now about some of the things that we're hoping to measure in Venus's atmosphere. And just because it's, it's what I'm personally really interested in, I'm going to be speaking about this with an emphasis on seeking signs of past water. So VMS will be carrying specialized gas processing instrumentation to enable a comprehensive and also sensitive investigation of noble gases in Venus's atmosphere. Noble gases are important and interesting because they're non-reactive. So they can record a long history of processing that occurs in a planetary atmosphere. They can record very early events, all the way through events that are that have occurred recently. They can also record the formation history of the planet by comparing the noble gases on Venus to the noble gas inventory of the building blocks that we expected Venus to form with. We might be able to get a sense of the materials that Venus formed out of. And by looking at what those materials are made out of, by looking at their volatile and water content, this might help us to understand how much water Venus formed with initially. Volcanism is another really important process that's relevant to, not just interesting geological activity, but also maybe the history of water on Venus, because water may have been outgassed through Venus volcanism over time. So in addition to helping us to understand the materials that Venus may have formed out of, noble gases can also help us to understand the degassing history on Venus. The figure here is showing you certain noble gases that are byproducts of radioactive decay processes that are expected to occur in Venus's interior. So for example, one of them is helium-4. Helium-4, so remember what I told you about hydrogen? It's really easily lost to space because it's a lightweight gas. Deuterium is also pretty easy to lose to space, but a little less easy. Helium-4 is also lightweight, so it's also pretty easy to lose to space. It doesn't stick around in the atmosphere very long. So what that means is that if you outgas it, you would expect it to have a relatively short lifetime in the planet's atmosphere. So if we see it, especially if we see it in great abundance, what that means is that there was a recent volcanic activity on Venus that recently put that helium-4 into the atmosphere. Argon-40 is another gas that we want to measure. That's another radiogenic decay product that would form in the planet's interior and be outgassed through volcanism. And it's continuously produced in the planet's interior. So by measuring it, and it doesn't escape to space easily because it's heavy. So if we measure it, we can get a sense of the integrated degassing over time. And xenon is really interesting because xenon has never been measured before at Venus. And by measuring xenon, it can tell us things about the interior sourcing of water and volatiles that may have occurred early on in Venus's history. So one of the most compelling pieces of evidence for past oceans on Venus, as I mentioned, is this D to H ratio. The prior measurements of D to H on Venus have indicated that it is surprisingly high. It is way higher than we would expect it to be if it had the D to H ratio it currently has when it formed. Somehow it evolved to have that high D to H ratio over time. And so this idea of the history of water loss has been put forward as a way to explain that. And we're going to be measuring the D to H ratio in great detail in a vertically resolved fashion. And that's important because prior measurements have shown us that the D to H ratio on Venus can actually vary with altitude, which is kind of unexpected. We don't fully understand why it would vary with altitude. So we're going to make at least 10 measurements throughout the atmospheric column of this important quantity to help us understand both, does it actually vary with altitude and how much does it vary with altitude? And also to provide this critical input to models that are seeking to understand the timing and quantity of past water that Venus may have lost. In the second half of our descent sequence, we're going to be entering the deep, mysterious atmosphere below the clouds. This is a very mysterious region on Venus because it's difficult to remotely sense it. Venus has such thick clouds; they're so opaque. It's just hard to access this region remotely. You can do it to an extent. I've done it myself from ground-based observations through what are called near-infrared spectral windows. And through those spectral windows, you get this sense that the atmosphere is very changeable and it's dynamic on very short, Earth daily timescales. And there seems to be these interesting spatial patterns in the distribution of gases that might imply interesting chemical conversion between gaseous species in the deep atmosphere that we don't fully understand. So this mysterious region is dynamic, and it's probably going to surprise us whatever we find down there. So when we go there and we make measurements in situ, I have no doubt that we're going to be surprised, but it's going to be really exciting because we're going on this voyage to this relatively unexplored region. Alrighty, so I've talked about some of the things that we're going to be doing in the atmosphere, but I haven't told you yet where we're going. So where are we going? So we're going to a place called Alpha Regio. That's our descent site. Alpha Regio is indicated here on this topographic map of Venus. This is topography from the Magellan spacecraft. You can see it indicated there in almost the middle of the slide. It's a type of terrain on Venus known as a tessera. Tessera across Venus are indicated with the white blinking outline that you can see here on this slide. What's really interesting about these tessera, well, they're geologically interesting in that they have this highly deformed they're highland terrain. You can kind of think of them as mountains. So the geology of them is interesting. They're also interesting because some folks have interpreted them as potentially older than the surrounding terrain. Most of Venus, based on crater counting records, is interpreted to be pretty young and pretty much the same age. Most of Venus's surface appears to be about 800 million years old, which I know doesn't sound young, but cosmically speaking, it is young. It's very young, actually. That's potentially due to a catastrophic volcanic resurfacing event that may have occurred planet-wide 800 million years ago. But these tessera may record a more ancient past because they may be older than the surrounding terrain. And that's really interesting because if there was a past habitable epoch on Venus, the evidence for that would have been obliterated throughout most of Venus's surface from that past resurfacing event. But maybe, at least in some of these tessera region, maybe they predate that resurfacing event. So maybe there's geological clues on these tessera that might be indicative of whatever Venus's more distant past look like. And we would like to know what kind of rocks these tessera are made out of. So let me just say a few words about a couple very broad classes of rock types. One of the goals we have for the mission is we want to use our camera to distinguish between broad mineral classes on Venus. And specifically, we're trying to distinguish rocks that are considered more mafic from ones that are more felsic. More mafic rocks are rocks that are magnesium and iron rich. These are rocks that form from volcanic eruptions. So solidified lava forms types of mafic rocks. An example of a mafic rock is basalt. And appearance-wise, they tend to be dark. They have low reflectivity. On the other end of the scale are felsic rocks, which are iron and magnesium poor, and they form from a different process. These tend to be more silicon-rich rocks. And the way these rocks form is from water-rock interactions and continent-building processes. So on Earth, when you subduct rocks at plate boundaries, and then you partially melt some of that material and it gets extruded in continent-building processes, you can form these more felsic rocks. An example of a felsic rock you may be familiar with is granite. Appearance-wise, these tend to be lighter in color. So what's really interesting about felsic rocks is what they imply about their formation history. They necessitate the existence of water-rock interactions, and they also require continent-building processes, which, from what we understand about them, requires plate tectonics. And from what we understand about plate tectonics, it requires water to sort of lubricate the plates so they can actually slide against each other. So if they're felsic rocks on Venus, that would be really, really interesting because that might suggest that the past history of Venus looks very, very different from its current state. So are there felsic rocks on Venus? Some people think there might be. This is a figure from a paper by one of our mission's co-investigators named Marty Gilmore. She's a professor at Wesleyan University. And what this is showing in this figure from one of her papers On the left side, that's a Magellan radar map of Venus at the Alpha Regio region where we're going, where the tessera region is outlined in that yellow. And on the right, that is a measure of surface emissivity. So how much heat the surface is emitting. Different types of minerals emit different levels of heat for the same temperature. And one of the things to notice is that the tessera region has an anomalously low emissivity compared to the surrounding basaltic plains. And one way to explain that anomalously low emissivity is that possibly the rocks are different in composition and felsic rocks is consistent with that lower emissivity. So again, we don't know if there are truly felsic rocks on Venus, but if there are, that would be really exciting. And so we're going to go to Alpha Regio and we're going to try to understand what the surface is made out of. Okay, so how are we going to discriminate between felsic and mafic rocks at Venus? Well, with our Vinci camera, our Venus Distant Imager camera, we're going to use a technique called a band ratio technique. And what that does is it takes the ratio of surface reflectance in a broadband filter compared to the ratio of surface reflectance in a narrow band filter that are chosen at wavelengths where you can discriminate between these different rock types. We've done on our team a proof of concept of this technique using a region of Australia known as the Pilbara, which is in Western Australia. I've been there myself and it's a really cool and really desolate area. So the Pilbara is interesting. And one of this region of the Pilbara here that's indicated here is a place that shows clearly defined boundaries of surface exposed felsic rock exposing ancient surface crust. Now here, what I'm showing you on the right is an example of using this Vinci narrowband broadband ratio technique that's analogous to the kinds of measurements we're going to obtain with Vinci. And here, what we've color-coded it is as the higher, brighter in color reflectivity rocks are color-coded green, and the lower reflectivity rocks are color-coded in purple, as distinguished with the band ratio technique. Now, the known boundary between the mafic and the felsic surfaces is indicated with that yellow outline. And you can see that this technique is doing a pretty good job of mapping the higher reflectivity rocks, that is the green ones, to within the yellow boundary, and the lower reflectivity rocks, that is the purple one or the more mafic ones, exterior to that boundary. So this is very encouraging, and we're continuing to work on this. So with all of this information that we hope to obtain with DaVinci, we may learn that there are multiple lines of convergent evidence that we obtain that might suggest that our solar system had at least 2 surface habitable worlds side by side for a large fraction of our solar system's history. Maybe even there's 3 habitable worlds if Mars was habitable too for a long fraction of time. So by comparing and contrasting the evolution of possible habitability on Venus and Earth, and possibly also Mars, I think we'll begin to understand habitability better as a general process, and also understand habitable planets as an evolving class of worlds with different possible evolutionary outcomes. And this now leads to another topic that's near and dear to my heart, which is exoplanets, planets and other solar systems. It's really exciting right now because observations of terrestrial planets are on the very near horizon with the recent successful launch of JWST, which I hope everybody on this call saw the amazing photo group selfie that JWST took of its primary mirror recently. If not, you should look it up because it's really cool. But that mission is going to be awesome. And DaVinci is poised to help us better understand exo-Venus planets that JWST may observe. Exoplanets are amazing, and we now know there are countless other solar systems in our galaxy. The broader landscape that our solar system sits in is breathtakingly complex, and we are just beginning to scratch the surface of what's out there. But what we now know is that most other stars have planetary systems. The video that you're looking at here shows just a small fraction of the thousands of exoplanets that NASA's recent Kepler mission alone discovered. Now, notice the temperature scale on the left side of this plot, and notice how many of these worlds are the temperature of Venus or even hotter. This is because Kepler discovered exoplanets using a technique called the transit technique. Transits occur when a planet passes directly in front of its host star from our point of view and blocks a small fraction of the starlight. So planets that are orbiting closer to their stars are going to be on shorter orbits, and they're going to transit more frequently. So it's easier to observe planets that are closer to their stars in short orbits compared to planets that are much farther from their stars that transit much less infrequently. This transit technique is also what JWST is going to use to study exoplanets. So it is likewise biased towards observing planets that are closer to their stars. So it's going to be observing more easily planets that are hotter compared to planets that are colder. And in fact, we think it's going to observe more kinds of exovenuses, we call them, than any other kind of terrestrial planet. So by studying Venus, we might be able to obtain ground truth data that may help us to someday interpret these exovenus planets that will soon be observed by JWST. And Venus's possible past habitability, which is so intriguing, also suggests that exovenuses may likewise be habitable too, and perhaps we can observe them at evolutionary stages akin to what Venus may have experienced in the past. So obviously we can't get into a time machine and go to Venus's past and see what it was like there, but exoplanets might offer us the next best thing by showing us examples of planets that may be in evolutionary stages akin to what Venus experienced in the past. Now, in this talk, I've talked a lot about, the possibility that Venus may once have been habitable, but I haven't actually said anything about, ideas that we have in the scientific community about why it may have been habitable or what may have enabled it to be habitable, because Venus receives twice as much energy as Earth does from the sun. So even when it formed, it was a lot hotter there than it is here. So how do you get a planet that's receiving that much solar energy to maintain habitable surface temperatures? Well, a quirk about Venus is the fact that it rotates really, really slowly. And a surprising fact is that this slow rotation may actually be relevant to enabling its early habitability. So how does that work? There was a recent study by one of my colleagues who's at the Goddard Institute of Space Sciences, Michael Way, where he ran a 3D climate model for a hypothetical habitable early Venus with an assumed Earth-like atmosphere. And what he finds is that slow rotation really dramatically changes the type of convection that you have in the planet's atmosphere. For fast rotating planets, you smear the clouds out into bands. And Jupiter is an extreme example of this. It's a very fast rotator. If you think of a picture of Jupiter, it's got those very, very banded clouds. Those form because Jupiter is rotating so quickly. But for a very, very slow rotating planet like Venus, the situation is different. You drive very, very vigorous convection on the planet's day side. You don't smear the clouds out. Instead, you're concentrating the clouds on the planet's day side. Clouds are very reflective. And in this case, we're talking about a hypothetical habitable planet. So these are water clouds now. So you have this surface of, bright white reflective clouds on the planet's day side. And what that can actually do is it can reflect enough sunlight back to space that it could, if this hypothesis is true, that you would reflect enough light back to space to cool the surface temperature of the planet down enough to maintain habitable conditions for potentially billions of years. So through this process, it's possible that our solar system had, these two habitable worlds side by side for a long fraction of time. And possibly through this mechanism, Venus may have even remained habitable up to several 100 million years ago, which is very cosmically recent, even though I know it doesn't sound cosmically recent. And while there are multiple plausible models of Venus history, including models of never habitable states, the reason why I brought up that slow rotation cloud-induced phenomenon specifically is that it turns out to be very relevant to the types of exoplanets that JWST is going to observe in the near future. So JWST can only observe planets orbiting around the dimmest, lowest mass stars, such as the star of the TRAPPIST-1 system shown here, which, if you're unfamiliar with this system, it's a system of 7 rocky planets orbiting a star that's much, much smaller than the sun. The small size of this star and the dimness of the star means that any planets orbiting in the habitable zone or interior to the habitable zone, where the habitable zone is the region around the star where you can have planets with liquid water on their surfaces, they have to huddle up really close to their star for warmth because the planet is so dim, or because the star is so dim. And so if you look at the scale of this TRAPPIST-1 system with the habitable zone and the hot zone and the cold zone, and then look at the scale of how it fits well within the orbit of Mercury within our own solar system in the bottom image, that gives you a sense of how close to the star these planets are. So what does this have to do with rotation rate? Well, when you have planets that are orbiting this close to the star, they become vulnerable to the impact of stellar tidal forces acting on the planet. This is similar to how tidal forces of Earth acting on the moon slowed the moon's rotation rate down over time until the moon got into a state called synchronous rotation, where it spins on its axis once every time it goes around our planet. We expect that planets that are orbiting close to these low mass stars that JWST is going to observe are going to be frequently in this kind of synchronous rotation regime or tidally locked regime where their rotation rate matches their orbital period. So they're going to be spinning quite slowly compared to Earth. And so we think that slow rotation is likely to be ubiquitous for the types of planets that we'll be observing for JWST in the near future, which orbit close to these low mass stars. And what's interesting is that this same tidally locked slow rotation phenomena that was studied for Venus has also been studied for exoplanets. And this phenomenon is expected to dramatically impact the climates of these planets orbiting these low mass stars. So by studying Venus, we may help to better understand this history on the planet next door. And by studying these exoplanets, we might better understand what happened to Venus in the past. So was it habitable or not? Well, I don't know. I wish I could give you the answer for that. But the data that we collect with our mission is going to help answer that question. And I think both possibilities are really interesting because both of them impact the way we're going to think about habitability. The history of Venus may help us to refine the parameter space in which we search for habitable worlds beyond the solar system. So here is a figure showing the Venus zone, which shows hot planets that are close to their star, and the habitable zone, which is the region, as I mentioned, around stars, where you can have planets with liquid water on their planetary surfaces. And traditionally, we consider the boundaries of the habitable zone to be the region where we might find worlds like Earth with surface water and temperate conditions. But if Venus was truly habitable in the past, then that implies that the boundaries of the habitable zone may be fuzzy, and there may be these habitable Venus-like worlds lurking in the so-called Venus zone. And even if Venus was never habitable, the processes that might have acted on Venus today, maybe they never did, but maybe they're acting on exoplanets. And so, this range of possibilities that planets can go one way or the other, I think by studying this diverse population of worlds, it's going to give us a much better understanding of these evolutionary outcomes that are possible for terrestrial planets. And since JWST can more easily observe these planets close to their stars compared to farther away, it's going to be biased towards observing these Venus zone planets, as I alluded to before. So we're going to probably be observing more kinds of exovenuses than any other kind of terrestrial worlds. And some of those planets in the Venus zone, maybe they're habitable, maybe not, we don't know. But it's going to be really exciting and fun to finally get the data. So in general, Venus helps us to answer questions that I think really lie at the heart of what it means to be a habitable planet. And as we search for potentially habitable worlds elsewhere, I think it's really interesting and important to remember that a once habitable world may be right next door to us. Fundamentally, understanding Venus really connects us to the notion that habitability is not stagnant and it does evolve over time. Better understanding how habitability on Venus was either lost or never gained a foothold will likewise help us better understand our own planet and the processes that did enable habitability here. So if we characterize the surface of Venus to understand its geology, if we study its atmosphere to find out what it's made of, if we understand its dynamics and its climate, piecing together this whole holistic picture of the planet next door, we're hoping to resolve these big questions of whether Venus may have looked more like Earth in the past, and if it did, what went wrong? Or maybe Venus never looked like Earth in the past, and in which case, why? Why is it so different from our own planet? Is it because it formed so close to the sun compared to ours? What other factors are relevant here? So now in the last few minutes, let me bring us back to the mission, DaVinci, and let me just summarize for you what we'll be doing through our hour-long descent through the atmosphere to help rewrite the textbooks on this exciting planet next door. Okay, so in the upper clouds, below 70 kilometers, we'll be using our VMS instrument and our VTLS instruments to measure the composition of the atmosphere in great detail, including interesting trace gases and isotopes and that D to H ratio that I've told you about, which is really important for understanding the history of water on Venus. As we pass into the clouds, we're going to be measuring those noble gases that I told you about: helium, neon, argon, krypton, and for the first time ever, xenon. These are going to provide new insights into how Venus formed and evolved. Since they're non-reactive, they can record a long history of processes that occurred on Venus. As we emerge below the clouds, we'll be using our Vendy camera to image the surface to search for reflectivity signatures that may be consistent with rocks that formed in the presence of past water. We want to understand the nature of that mysterious Alpha Regio tessera region, and we want to understand if there are truly felsic rocks or granitic rocks that might be lurking, in the terrain that maybe harken back to a more hospitable epoch in the past. Continuing into the deep atmosphere, we'll continue to make regular cadence measurements of interesting trace gases, isotopes, including the D to H ratio. As I told you before, we'll get at least 10 new measurements of the D to H ratio throughout the atmospheric column. So then we can feed those into models, trying to understand, what happened with water on Venus in the past. In the deepest atmosphere, we'll be looking for chemical gradients near the surface. We're going to try to understand surface-atmosphere interactions. And also our student collaboration experiment, VFOX, is going to measure the abundance of near-surface oxygen. Lastly, as we get very near the surface, in the lowest 2 kilometers, Vendy will provide surface topography of Alpha Regio at sub-meter scale. It's going to provide the first 3-dimensional view of a tessera. And then wrapping around all of these measurements, our Venus Structure Investigation Experiment, or VASI, will measure pressure, temperature, and winds to provide context for the rest of our experiments. So in a nutshell, that's what we're going to Venus to do. So I hope that this talk has helped you to better understand our mission. And if there's time, I'm happy to take questions. Thanks.
Oh, there's definitely time. Thanks, Dr. Arney. That was great. That was, you touched on a lot of the stuff that I was really hoping that you would go over today. And, I guess I'll start with one of the questions, because you did talk about plate tectonics a bit and felsic rocks. But one thing, I guess maybe I missed it, but what do the mountains on Venus look like? I mean, I imagine that you're not going to have, plate tectonics make some rather large mountains on Earth, but that's got to be a whole different equation when you're talking about it on Venus, where, it's raining sulfuric acid and it's hot and it's, it's not a pleasant place.
Yeah. So I mean, the surface terrain of Venus is volcanic rock, basically everywhere. There's basalt pretty much everywhere. All of the volcanoes are all over the surface of Venus, and ancient volcanoes, and maybe currently active volcanoes, because Venus, there are suggestions that Venus is currently still active. But Alpha Regio and these tessera, these highland regions, they're interesting because they may be remnants of ancient continents. So you can kind of think of them as like, so the word tessera comes from a word that means a tile mosaic, which I think they probably gave to these features because they have complicated geologies on their surfaces. They're very folded. So think of a very complicated mountain range. That's kind of the surface terrain we're landing on. We're not landing on smooth rolling plains with our descent probe. We're landing on a very challenging terrain, which is okay because we're not required to survive landing. But it's definitely not the kind of terrain you might pick if you wanted to, have a soft, nice, cushy, safe landing and guarantee survival on the surface. So that's sort of how you can picture what these are like. What's also interesting about the highlands on Venus is, if you think about the mountains on Earth, we have snow-capped mountains, right, with beautiful snows on them. Well, obviously, there's no water snow on Venus. Maybe there was in the past, but what instead people see interesting evidence for a different kind of frost that occurs on Venus, and it's a heavy metal frost because it's such a different temperature regime that you actually get, not condensation of water, because water can't condense on Venus, but instead these condensation of these exotic heavy metals that may be capping some of the higher elevation mountains, which is, I think, kind of wild to think about. So that's some of the characteristics of the mountainous regions on Venus.
Heavy metal frost. I'm really, I'm digging that. That's great. Another question from Franco here. The Parker Solar Probe just did a little swing by Venus here recently, and actually took some interesting pictures. Mm-hmm. Can you add a little bit about, because I think we saw like some surface images here. Can you add a little bit about what we saw? And we are going to be having the guys from the Parker Solar Probe talk with us here soon. So it goes hand in hand.
Yeah, I wish I included one of the photographs from that paper in this talk, but I didn't do it. So Parker Solar Probe imaged a piece of Venus's surface called Aphrodite Terra, which I don't know if you can see my mouse, but if you can, it's this region here. This is Aphrodite. And an interesting fact about Venus that I think a lot of people don't realize is the clouds are not completely opaque at all wavelengths. If you look at Venus on the night side in the near infrared, there's actually a part of this spectrum where you can see thermal radiation upwelling from the surface and also the lower atmosphere, and it gets to space. It's scattered a lot in the clouds because even though the atmosphere is not absorbing at these wavelengths, it's still extremely scattering. So there's an extremely large scattering footprint of about 100 square kilometers. So you can't see small scale features, but you do get radiation from the deep atmosphere and also the surface. And people have been using these near infrared windows since they were first discovered in the 1980s. And they've provided this glimpse of the deep atmosphere. Let me try to go to a slide of the deep atmosphere. There we go. So we get these enigmatic glimpses of this very deep region of the atmosphere through these spectral windows. And I've done this myself with ground-based observations using a telescope here on Earth in New Mexico called the Apache Point Observatory, where I've measured and mapped the abundances of trace gases below the clouds through these windows. What's cool about the Parker Solar Probe is that they're extending the wavelengths where you can sense Venus's surface. So previously, we knew that we could sense Venus's surface between and the lower atmosphere, between roughly about 1 and 2.5 microns, which hopefully, since this is an audience of amateur astronomers, that makes sense to you all. And now we're able to sense Venus's surface at shorter wavelengths, even pushing into the optical wavelengths. So Parker Solar Probe made the very first measurements of Venus's surface remotely above the clouds at optical wavelengths, which is pretty cool. And what it was measuring thermal radiation on the night side. As I mentioned very briefly early in this talk, Venus's surface is hot enough that it's actually emitting, some amount of heat at optical wavelengths, at the wavelengths that our eyes can sense. So this was actually picking up some of that heat that Venus's surface is putting out in the optical, which is cool. And so it'll be really interesting in the future to see what people determine about maybe some of the minerals that we might be able to sense at these new wavelengths that we know we have access to. I'm not a geologist myself, but and there's we're making measurements with DaVinci in the 1 micron region because that's a good region for discriminating between mafic and felsic rocks. But someone who is a mineralogist or a geologist might be able to say, oh, hey, in these optical wavelengths that the Parker Solar Probe can access, hey, we can discriminate between these minerals. So it'll be cool to find out what we learn about Venus at those wavelengths.
Can't wait. We had another interesting question from YouTube here. Tio Rico says, welcome, Giada. Do you have any inspiration from the old Jacobson Observatory at UW, or just admire it as a relic? It was already 66 years old when he first visited that observatory 50 years ago.
Oh, that's such a great question. I was a grad student at UW, and the grad students didn't really use the Theodore Jacobson Observatory. I'm sorry to say, but I thought it was so wonderful how it was used by the community and by the undergrads there. I don't think these kinds of observatories are relics because I think they're really, really great for science engagement and public engagement, even if they're not actively being used for science, like by professional astronomers. It was still used by the undergrads for class projects, and they still used it for a lot of outreach activities, which I thought was wonderful. I was involved with the planetarium activities at the University of Washington. I was planetarium coordinator there for a year, which was quite a lot of work. So I definitely have a very deep appreciation for public outreach.
Oh, that's cool. Kurt Zapatello asked a question here too. He goes, I'm not sure if this is your expertise, but how does the laser spectrometer determine the isotopes? Would not the same element give off the same spectral signature no matter what isotope? Also, if you find suspected granitic composition rocks, any plans on another test?
Yeah, good questions. I wish I had one of the people on this call who builds instruments, because I feel like they'd be able to better understand that better able to answer that question. So VMS is going to be measuring the masses of these compounds, and so it has the precision to be able to differentiate the masses of the gases that we want to go after in Venus's atmosphere. VTLS, let's see if I have a slide on that. That's the best slide. It's going to be using lasers that are tuned to sense the particular gases that we have chosen in advance that we want to go after in Venus's atmosphere. So these lasers are going to be sensitive to the particular gases that we want to go after, which are listed here on this slide. And this includes the D to H ratio. And then VMS is going to be measuring these mass spectra to measure both known gases, but also to discover new gases. And if I was a mass spectrometer person, I could give you a much deeper answer, but I am not a mass spectrometer person. I just work with them. Also, the question about granitic rocks. Yeah, that's a really great question. So what would we do to follow up if we thought we saw granitic rocks? I mean, certainly one of the things is that we're not the only mission that's going to Venus. There's this whole, it's exciting because there's this whole fleet of Venus missions that are going to be going there in the future. There's DaVinci, which I've talked about. There's also another NASA Venus mission that was selected called Veritas. And one of Veritas's instruments is a camera that's going to be mapping Venus above through those near infrared windows that I was talking about in response to that earlier question. And through those near infrared windows, it's going to be looking for surface emissivity signatures that are consistent with felsic rocks. So again, same goal here. We also have our visor camera on our flybys spacecraft that's going to be doing the same thing, just not quite as complete geographic coverage as Veritas is going to have, because it's an orbiter that's going to be circling Venus, doing this for a long time with a great camera on board that's going to be looking for felsic rocks. So it might be able to help corroborate some of our in situ observations that we make below the clouds at Alpha Regio, and also look for felsic rocks on a more global scale. There's also a European mission to Venus launching in the early 2030s called Envision. Envision also has a spectrometer on board that is also going to be looking through the near infrared windows. It's looking for these heat signatures on the surface emanating upwelling through the clouds. Also, one of its goals is to try to better understand the surface composition of Venus. So hopefully, interpreting all of these data sets together will give us a more complete understanding of what the surface is composed of. And in the more distant future beyond that, I hope eventually we'll send some landers there that can survive for, a meaningful amount of time to try to measure the surface in situ. But that's farther off, and there's no current plans for that.
Well, that's great. Again, thank you so much for this. I don't see any other questions coming up here. So, you have one? Oh, good.
I have a question.
Tell me, Shannon. Good, please.
Well, you've talked about the bulk of the science in this mission is going to happen in an hour during the descent phase, and you're descending through an atmosphere that at the bottom is more than twice the crush depth of a nuclear submarine. So that's some pretty dense air. Is there not some strategy or plan to maybe slow the descent so you have more than 1 hour? Could you induce some kind of drag to just allow it to take more time?
So part of the complication with that is we have to talk to our spacecraft during the descent, and they're only going to stay aligned for a certain amount of time before the spacecraft goes over the horizon. So in that sense, we only have a limited amount of time during the descent before the spacecraft is over the horizon. And even if we continue to survive, we have nobody to talk to and transmit the data back to Earth. So that's one constraint. And actually, we have a parachute, but we jettison it halfway down through the descent. So we do slow down intentionally at first. But so what this is showing is this is a timeline of our mission descent, where here we're entering the atmosphere. We've deployed our parachute here. Here, this kink in the descent profile, that's where we get rid of the parachute. And the reason why we do that is because at that point, the atmosphere starts to become so thick that the atmosphere itself starts to slow us down. So that if we continue to hold on to that parachute, we would take too long to descend through the atmosphere, and our spacecraft would leave and we wouldn't be able to talk to it anymore by the time we get to the surface. So we jettison the spacecraft, but we do speed up, but then we start to slow down because the atmosphere gets thicker and thicker and thicker, although we are still touching down pretty quickly at 13 meters per second onto hard mountainous rocky terrain. I would love to say that we could take, more time, or we could definitely survive on the surface, but we're very excited to have an hour.
Would it be possible to have something like a black box that stores the data and then it could transmit on a later pass? So you've got a hardened part that can store data, so that even if the overall descent module doesn't survive, this black box can still transmit whatever it picked up.
Yeah, that's a fascinating idea. That's
that they didn't do, Shannon.
Yeah. It's a fascinating idea. I love that. But it's not part of the mission design.
We had a question too about will we get a definite answer for phosphine on this mission?
Let me go back to BTLS. So we have notionally, we have 3 lasers on BTLS. We are currently studying the addition of a 4th laser that could measure an additional interesting gas. So it could be phosphine, but it doesn't have to be. We're actively discussing this on the science team, both the feasibility of adding the 4th laser, and also if we do add a 4th laser, what would we want to go after? Because these lasers, they're tuned to measure specific things. So we kind of have to pick in advance what we want to measure. And this is a discussion that we would have, both internally in our science team, but we also want to reach outward to the broader Venus community to get their input as part of the process. So this is ongoing still, and nothing has been decided, but it is something we're discussing.
Great. Any other questions? I didn't say anything else. Anything else from the panel?
No.
No.
All right. Well, thank you, Dr. Arney. We really appreciate this. This is a great talk. I mean, really interesting. It was everything I wanted to know about Venus. And, I think Mars is really boring, honestly. I just think it's just like a dead planet. Venus is not. Venus is anything but. It is, it's so much like Earth. And I hope that, someday that we can maybe step foot on there too. I think it's a long ways off, but someday. And so we'll stick a fork in it tonight. Thank you, Dr. Arney. Don't forget that next month we're going to be talking about NASA's Parker Solar Probe mission, and we'll do that all same bat time, same bat channel. So until next time, thank you, everybody, and we'll see you soon.
Thank you very much.
Bye-bye.
Thank you very much. Good night.
Good night.